All right, this is podcast 5.1 for AP Chemistry, and we're going to talk about liquids and solids and everything you ever wanted to know about them. Intramolecular bonding is bonding that occurs within the molecule. So we're talking how atoms are held together when we're forming these molecules. Intermolecular forces are forces that exist between molecules. So intramolecular was within the molecule, intermolecular is outside of the molecule. This is the reason that we see changes in states of matter. So the reason that we see things go from a solid to a liquid to a gas. Here's an example of what we're talking about here. We have hydrogen bonding, and we'll talk about what that is in a second. But hydrogen bonding in water is a type of an intermolecular force. So water molecules are held together, and that's represented by these dotted lines here, by hydrogen bonding. So the attractions between the molecules is intermolecular forces. What's holding the hydrogen to the oxygen, those are your intramolecular bonding forces. So our example problem here, which are stronger, intramolecular bonds or intermolecular forces? And the answer you would want to pick are your intramolecular bonds, because it's a lot easier for you to make something go from a solid to like a liquid to a gas. And all you're doing there is you're changing the intermolecular forces. You're breaking those forces between them. You're overcoming them to change it from a solid to a liquid to a gas. It's a lot harder, though, if we think of hydrogen and oxygen within water. It's a lot harder to actually break the bonds and get those hydrogens away from the oxygen. So the intramolecular bonds, the ones that hold the molecules together, are a lot stronger than the intermolecular forces that we'll be talking about. So here are the types of intermolecular forces. We kind of classify them into ionic and covalent. So if you have an ionic compound, you have ionic intermolecular forces. If you have a covalent compound, you can have dipole-dipole, or you can have London dispersion forces. Dipole-dipole exists if you have a polar molecule. London dispersion forces exist if you have a nonpolar. And then hydrogen bonding is a specific type of dipole-dipole. It's a special type that occurs within some molecules. So dipole-dipole forces, you again have to have polar molecules, and those polar molecules have dipole moments. And I'll show you a picture in a second, but remember those dipole moments are where you have that partial positive, you have the partial negative side. So we have an uneven sharing of electrons. Molecules with dipole moments can attract each other electrostatically by lining up so that the positive and negative ends are close to each other, and that's how they're held together. Keep in mind, though, that these are only about 1% as strong as the covalent or ionic bonds that are actually holding the molecule together. So these dipole-dipole forces are not nearly as strong as the covalent or ionic bonds that are holding the molecules together. Here's a picture that shows that. So you can see here's like the partial positive and the partial negative and how they can attract each other if they line up opposite. Here's another way they could line up. Again, just like you can have an attraction, you can have a repulsion. So if the two negative signs are lined up, they'll repel each other, just like they would here. So dipole-dipole forces, you have to have a polar molecule in order to have them. Hydrogen bonding is a specific type of dipole-dipole force, and it's actually a pretty strong type of a dipole-dipole force. So what happens is there's a hydrogen that's bound to a highly electronegative atom, and those highly electronegative atoms are nitrogen, oxygen, and fluorine. So in order for you to remember the atoms that do hydrogen bonding, you can remember ET, phone home. So E.T., obviously, I don't know if anybody has seen it, but the movie E.T., and then phone home, so fluorine, oxygen, and nitrogen. You have to have those elements bonded to a hydrogen in order to have hydrogen bonding. So here's your example. The covalent bonds are your intramolecular bonds holding the hydrogens to the oxygen, but the dotted line here represents the hydrogen bond that's existing between the hydrogen and the oxygen. So the hydrogen bond occurs if you have hydrogen attached to fluorine, oxygen, or nitrogen. And that's just a really strong type of dipole-dipole force. The other type that was mentioned was the London dispersion forces. And London dispersion forces happen when you have nonpolar molecules. So usually you think of diatomics as being nonpolar. What happens is you get an instantaneous dipole that occurs and it occurs accidentally in a given atom, and it induces a similar dipole in a neighboring atom. And then it just kind of becomes this chain reaction of positive to negative, and because this is negative, then this becomes positive, and then this becomes negative, and you just get this big chain reaction of inducing these positive and negative poles when you normally wouldn't have them. London dispersion forces do occur in all molecules, and that includes nonpolar ones. So in your nonpolar molecules, this is the only type of force you would have between the molecules. In your polar ones, you'll have dipole-dipole. But this is a really important force to remember for right here. This becomes pretty significant when we start building larger atoms or molecules, because we have so many more electrons that we're dealing with. When they induce these poles, it actually becomes quite a strong force that holds these molecules together. So not as significant in the smaller molecules or atoms, but when we get to those big and like maybe oil molecules or things like that, you have those really large molecules. This does make a big difference in how these molecules are held together and the forces between them. So melting and boiling points can be affected by the type of intermolecular forces that we see within molecules. So in general, the stronger the intermolecular forces, the higher the melting and boiling points. And that should make sense to you, because if we have some molecules that are being held together by hydrogen bonding, for example, and then we have another one that's just being held by London dispersion forces, it's going to be a lot harder to break those intermolecular forces with the hydrogen bonding than it is with the London dispersion force molecules. So what we're going to see is that when they just have the London dispersion forces, that it's going to have a much lower melting and boiling point. It's going to be a lot easier for them to break those forces between the molecules and melt and then boil, whereas it will be a lot harder to do that in something that has those really strong intermolecular forces. The examples that they're showing you here are of boiling points. So we have some different substances. We have hydrogen and oxygen, so we have the water. Hydrogen fluoride, we have ammonia, and then we have methane. And if you look at these and we examine the different types of intermolecular forces that are in them, this is just a nonpolar molecule, so this would have London dispersion forces, and that's it. So it has a relatively low boiling point as compared to these other things. Ammonia, though, has a hydrogen attached to a nitrogen, so this has hydrogen bonding. This also has hydrogen bonding, and it's attached to even a more electronegative in fluorine. So both hydrogen bonding, but fluorine is more electronegative, so this is also hydrogen bonding. Water is a special case to that, because you might be thinking, well, oxygen is not as electronegative as fluorine, but this actually has two cases of hydrogen bonding. So this is hydrogen bonding times 2, because both of those hydrogens are there, so you get hydrogen bonding twice in each water molecule, which is why it says it has such a high boiling point compared to these others. So London dispersion forces has a really low boiling point. Hydrogen bonding bumps up the boiling point, and then if you have hydrogen bonding times 2 like you do in water, you're going to see a much higher boiling point. So you can use these intermolecular forces to kind of rank what you believe the boiling points or melting points of these substances would be. Let's see, which has the stronger intermolecular forces, and they want us to explain. So if we think of nitrogen, and if we were to draw it out, nitrogen is a diatomic. It's going to be nonpolar, which means it's only going to have London dispersion forces as its intermolecular forces. Water, on the other hand, is going to have hydrogen bonding like we just said, and it's going to have 2 times the hydrogen bonding. So not just once, but twice. So this one is definitely going to win out as the one that has the stronger intermolecular forces because it hydrogen bonds. The nitrogen is a nonpolar that'll just have London dispersion forces. All right, example problem 3. Two possible Lewis structures for the formula C2H6 are drawn below. Compare the boiling points of the two molecules. So their formulas are the same, but we can arrange the atoms in a different order. And it's asking us to compare the boiling points of each. So we're going to try and identify what types of intermolecular forces will we see with the two different structures that we have here. So in this top one, I have a polar molecule. I also have an oxygen attached to a hydrogen, or a hydrogen attached to an oxygen is probably how we should look at it. That means I have hydrogen bonding. If I look at this one down here, I have a polar molecule still, because this will cause it to be polar, but that oxygen is not attached to a hydrogen. So this is just dipole-dipole, which means I would expect that this substance, ethanol, should have the higher boiling point because it has the stronger intermolecular forces. All right, example problem 4. Which gas would behave more ideally at the same conditions of pressure and temperature? So we have carbon monoxide or nitrogen. Carbon monoxide, if we were to draw it, would look like this. Nitrogen again would look like this. So when we're looking for gases to behave ideally, we do not want them to have intermolecular forces. We don't want them to interact with each other. This one is a polar molecule. The oxygen is more electronegative than the carbon, so there's going to be a partial negative charge towards the oxygen and a partial positive charge towards the carbon. That means that this has dipole-dipole interactions. The nitrogen, if we remember back, is just London dispersion forces. So the weaker the forces, the more ideal it would be. So the gas that would behave more ideally should be nitrogen because it has weaker intermolecular forces. All right, we're going to skip to liquids. So general properties. Liquids have low compressibility, lack of rigidity, so we know all of this. High density compared with gases. We know all of these things. There are a couple properties of liquids, though, that you need to be familiar with. The first one is surface tension, and surface tension is the resistance of a liquid to an increase in its surface area. The reason that we know that liquids have high surface areas and how you can see that is if you were to dump water onto the table, or any liquid for that fact, most of them are going to bead up. And the reason they do that is they're trying to increase their surface area. Or not try and increase, they're trying to decrease their surface area. They're more attracted to each other than they are to whatever they're sitting on. So in this case, this is water. We can see why water beads up here is because it has a really high surface tension. That's the same reason that you can see bugs that can walk on water. Or you can set a paper clip on water and it just kind of floats there. That's the surface tension of water. They have a very high surface tension, so there's a great attraction between the water molecules that makes it harder to kind of break the force and get through the surface. Capillary action is another property that you need to know. Capillary action is the spontaneous rising of a liquid in a narrow tube, and I'll show you a picture in a second of what that looks like. But there's two terms that go along with that. There's cohesive forces and adhesive forces. The cohesive forces are what they're referring to as the intermolecular forces, and that's among the molecules in the liquid. So if you have a really high cohesive force within that liquid, that means they're really attracted to each other. The adhesive forces are the forces that we would observe between the liquid and their container. So cohesive is within itself, adhesive is between the liquid and the container. And here's a picture that you can see capillary action. The diameter of the tube is decreasing as we go across here, and you can see that the level of the liquid is rising. So the narrower the tube, the higher the liquid is able to climb. But that's capillary action. It just spontaneously is rising up the tube on its own. They're not forcing it to go up there. That's just something that it does. Here's an example of what it looks like, and you know water looks like this, for example, when we pour it into a graduated cylinder. So water in glass forms a concave meniscus due to strong adhesive forces. Water is actually very attracted to the glass when you dump it in there, which is why it kind of climbs up the sides. There's really strong adhesive forces, so the interaction between the liquid and the glass that it's in causes the liquid to kind of climb, or the water to climb up the sides a little bit. Glass is a polar substance, so the polar water and the polar glass really like each other, and there's a great attraction between them. If we were to dump mercury into a glass tube, we would see the opposite. So you'd see it wouldn't be climbing up, it would actually be kind of curved like this. And the reason that is because mercury is nonpolar, the glass is polar, so there's no attraction between them. They're two different types. And so the cohesive force with the mercury is greater than the adhesive forces that we'd see between the mercury and the glass. And this is a big slide that just says, how can you predict if a liquid will have a strong or weak adhesive force? You're looking for the interactions or the types to be the same. So when we were looking at water and glass, we knew that they would have a strong adhesive force because water and glass are both polar. So they're going to be very attracted to each other. They both have dipole-dipole forces. The mercury, on the other hand, is nonpolar, so it just has London dispersion forces, and the glass is still dipole-dipole. So since they're not the same, their attraction for each other will be less, and that's why the mercury wasn't attracted to the glass. Viscosity is another property of a liquid. It's the measure of a liquid's resistance to flow, and here's some examples of liquids pouring out or not pouring out in the case of those two. Liquids that have large intermolecular forces or molecular complexity. So that means when you get those really long chains of oil, they are really, really long molecules and very, very complex. They tend to be highly viscous. So the larger your molecules and the more they're attracted to each other, the harder it is for the liquid to flow. Jumping to solids. Solids can have two types. There's amorphous solids and crystalline solids. Amorphous solids are very disordered in their structure. There's no pattern to how they're put together. An example of that is glass. Crystalline solids, on the other hand, are very ordered. They have regular repeating patterns that we can see, and the example for that one is sodium chloride. There's also subtypes to crystalline solids. So with a crystalline solid, you can have an ionic solid, a molecular solid, and an atomic solid. And then under atomic solids, there's even more types. So ionic solids are where you would see ions at the different points of the lattice, and I will show you a picture, but you should already be looking at it in your packet. So for example, the sodium chloride, you would have sodium ions and chloride ions at each of the points of the lattice. The molecular solids, those are like ice. So if we were to build ice, you would see the molecules, each individual molecule of water at each point. And then atomic solids just have atoms. And usually you think of metals when you think of atomic solids. So in our picture here, we have the atomic solid would be diamond. So we have diamond at each of these points on the lattice. Sodium chloride is our ionic solid. And you can see we have the sodium ions and then the chloride ions at each of these different points. And then here's your molecular solid where we're using water to build whatever structure that we have. So those are the three types of crystalline solids. Within metals, there's kind of two different bonding theories or models you could use, but they both say the same thing. So the electron C model is a more general model. It just talks about having these nuclei of these positive nuclei of the metals kind of around, and then you would have the electrons that are just able to flow from atom to atom. They don't stay with whatever atom they come from. They're just kind of flowing freely from atom to atom. So that's the sea of valence electrons. The other one that kind of gives you more of an explanation as to why that happens is the band model for magnesium. Well, here's the band model for magnesium, but it's called the band model, and it's using the molecular orbitals. And you can see the MOs here. So remember, this is where we take the atomic orbitals and we build molecular orbitals when things bond. Well, with the metals that we see, it ends up that eventually when they're creating these molecular orbitals, when they're bonding, it almost ends up as just this continuous band of space for these electrons to travel in. So at some point, all the molecular orbitals that are being formed just create this continuous band, and that's how the electrons are able to flow and move from atom to atom and all around the surface of the metals. So back to the classification of solids, we had the ionic solids, which we talked about as the NaCl. The molecular solids was ice. Atomic solids can also be broken down into metallic, network, and group 8A. And you can read those more as you want, but there's lots of different ways that we can classify solids. And then this table just gives you some properties about them. Melting point, boiling point, is it high or low? Are they good insulators? Are they good conductors? What do we see? So this is all about solids. Metal alloys also goes along with those solids. There's two types. There's substitutional alloy and an interstitial alloy. Alloys, remember, are just a mixture of metals. They're not reacting. They're just mixed together. The substitutional alloy is when you take metal atoms and they're replaced by something of similar size. The interstitial alloy is when you fill in holes with smaller metal atoms. I don't know what happened there. So if we go to the next slide, you can see a picture of what we mean. So this would be the substitutional alloy. We're taking the zinc atoms and we're replacing the copper atoms. And then here would be an example of the interstitial. You can see that we have the irons. The iron atoms are all packed in really tightly together. And then in those little holes, we're filling them in with carbon atoms. So these are the ways that we build some of those alloys like brass and steel that we use every day. Liquids, the behavior of a liquid in a closed container. So I have this flask here, and let's say I just filled it with water. When I initially stopper the flask and close it off to the outside, what I would see is that the liquid level would go down because initially there's really just evaporation. So what you're going to see is the liquid level will go down, and because there's a lot of evaporation going on. Eventually, though, we're going to see that the liquid level stops dropping and it stays wherever it's at. It stays the same. And the reason it stays the same is because the rate of evaporation and the rate of condensation are the same. They've reached an equilibrium. So the number of molecules that are going into the gas phase are equal to the number of molecules that are coming back into the liquid phase. And it's this continuous cycle. It doesn't just go and stop. Equilibrium keeps on moving. We still have evaporation. We still have condensation. It's just the rate of those two processes are the same. And you can see a picture of that illustrated right here in this diagram. So the rate of condensation initially is pretty low. That's when it first starts. So you can see evaporation stays constant, but we need the rate of condensation to come up and meet it. So as those molecules start evaporating, they also start condensing back, and it starts this cycle. And when that two rates equal each other, that's when we're at our equilibrium vapor pressure. The definition of vapor pressure is the pressure of the vapor present at equilibrium. That's pretty self-explanatory there. The system is at equilibrium when no net change occurs in the amount of liquid or vapor because the two opposite processes exactly balance each other. That is what we just said, that the amount of liquid doesn't change because the rate of evaporation and the rate of condensation are going at the same speed. Vaporization and evaporation are two different things, although they're sometimes used interchangeably. Vaporization is the change from a liquid to a gas at the boiling point. Evaporation is the change from a liquid to a gas below the boiling point. So just to know the difference between the two. You also need to know the term heat of vaporization or enthalpy of vaporization, whatever you want to call it is fine. It's abbreviated delta H VAP, so the heat of vaporization. And what that is, it's the energy required to vaporize 1 mole of a substance at 1 atmosphere of pressure. So we can look at those. Liquids with high vapor pressures evaporate easily. They are called volatile substances. So when you have things that like to go into the gas phase pretty easily and pretty quickly, those are your volatile substances. Vapor pressure decreases with increasing intermolecular forces. That, if you stop and think about it, makes sense, because if you have a really strong intermolecular force that is holding your liquid molecules together, they are not going to want to escape into the gas phase, nor will they be able to escape into the gas phase. So the stronger your intermolecular forces are, the harder it is for those molecules to go into the gas phase, which means the less vapor you are going to have above your liquid. So vapor pressure decreases with increasing intermolecular forces. If you have bigger molecules, you're going to have bigger London dispersion forces, which will hold your molecules together. And also, if you're dealing with a more polar substance, you're going to have those dipole-dipole or hydrogen bonds that are going to hold your liquid molecules in to the liquid phase, and they're not going to be able to escape to the gas phase. This is just a picture that illustrates how they can measure vapor pressure. This is a vacuum, so the pressure in the atmosphere is 760 torr, and then they can fill it. What they would do is they would inject water vapor, which is just gaseous water, into the tube down here, and it would float its way to the top, and they would be able to read the vapor pressure on each of these. Vapor pressure increases significantly with temperature. So the more energy you provide a system, the more energy those molecules are going to have, and the easier time they're going to have escaping into the gas phase. So your vapor pressure will go up if you have a higher temperature, because those molecules have more energy and they're going to be leaving the liquid phase to go to the gas phase. At higher temperatures, more molecules have enough energy to escape the liquid phase, which is what we just talked about, so you have the higher vapor pressure. Okay, this is a diagram that's taking vapor pressure versus temperature, and what we're seeing here are at 760 torr, these would end up being the boiling points for these three different substances. So if we looked, we have diethyl ether, ethanol, and water. Diethyl ether has just London dispersion forces. So it's here. It has a very low boiling point because there's not very strong intermolecular forces holding it together. Ethanol has hydrogen bonding, so the boiling point actually jumps up quite a bit. Water also has hydrogen bonding, except remember it has 2 times the hydrogen bonding. It has 2 hydrogen bonding hydrogens. So that's why its boiling point is even higher than ethanol's. So we can look at these substances and compare intermolecular forces and be able to tell about vapor pressure, boiling point, freezing point. We can get a whole bunch of information about these things. The other thing that you like to see or look at sometimes are called heating curves, and these should look familiar. This is the heating curve for water, and what a heating curve does is it shows the temperature of a substance versus time. So we're heating this substance up. What you're going to see then with a heating curve, and most of them will look like this, they will have the same 5 different areas. The first thing you're going to do is just heat up the ice. So we have just ice right here. Then we have ice and water because it's going through a phase change. So right here it's going through a phase change. And this is called the heat of fusion. So the energy it takes to melt ice, that is called the heat of fusion. Fusion, melting, that's what goes here. Then we have the water heating up, and then we have the water boiling, and this is where we would see the heat of vaporization for the water. And then we have just the steam. So when a phase change is occurring, notice that the temperature does not change. The temperature holds constant because that energy that's being applied is going into breaking those intermolecular forces. When we are not going through a phase change, that's when we see the temperature increasing. So we're just giving the substance more energy, and then we see that as a change in the temperature. So phase changes do not have a change in the temperature. Just heating up the substances do, and make sure that you know that this is the heat of fusion and this is the heat of vaporization. So which would you predict should be larger for a given substance? Oh, the heat of vaporization or the heat of fusion. If you remember back or look back in your packet at that picture that we were just looking at, what you're going to see for most substances is that the heat of vaporization is a much longer line as compared to the heat of fusion. And the reason that it's a longer line is because it takes more energy. And more energy corresponds to more time it takes for it to go through that phase change. So the heat of vaporization should be larger for a substance because it takes more energy to transform a substance from a liquid to a gas. It takes a lot more energy to break those intermolecular forces to get it from a liquid to a gas. Phase diagrams are the last thing we're going to talk about. Phase diagrams are similar to heating curves, except we get to see all three of the phases at one time. So it's a convenient way of representing the phases of a substance as a function of temperature and pressure. So we're going to have temperature and pressure, and we're going to see all the different places where we would have a solid, a liquid, and a gas. The triple point and the critical point are two important kind of vocab words or points on these phase diagrams that you need to know. The triple point is the temperature at which all three phases exist simultaneously. So there will be a point when we will see on this next slide when all three lines, it won't look like that, that was horrible. It might look like this. This point when all three lines are touching is called the triple point. That's the temperature and the pressure at which I can have a solid, a liquid, and a gas at the same time. The critical point is always between the liquid and the gas phase. This line goes indefinitely up. It just keeps going. The liquid and the gas phase, however, stops. At this point, it becomes what they call a superfluid, and it's really hard to distinguish between a liquid and a gas. So it's kind of this crazy substance right here past the critical point. But we're going to look at carbon dioxide and water. So the first one is carbon dioxide here, and you have both of them side by side so you can compare. But some important parts that we need to point out here. Here's the triple point for the carbon dioxide phase diagram, and you can see that that would be at negative 56.6 degrees Celsius, and then the temperature would be 5.1 atmospheres. Here's the critical point way up here. This line extends indefinitely. If you pick a pressure and a temperature that fall on these dark lines, you will have an equilibrium point where you would see both these phases. So if I picked a point right here, I would see both solid and liquid at the same time. You also can predict what you would see if you were to change some, like if you were to hold the pressure at 72.8 atmospheres and just increase the temperature, you could predict the phase change that you would see. So I know that if I held the pressure at 72.8 atmospheres of carbon dioxide, and I increased it from like -60 to -50, I should see the carbon dioxide go from a solid to a liquid. So this is a way that we can tell what phase change these substances will go through. And this is another reason. Here is normal atmospheric pressure, 1 atmosphere. You can see why carbon dioxide, dry ice, goes from a solid to a gas. It sublimes. The liquid phase cannot exist at this pressure. So that's why we see the sublimation of dry ice. We see it go from solid to a gas and it skips the liquid phase. So you actually can get quite a bit of good information out of looking at these phase diagrams. The last thing I'm going to point out, do you see how this is kind of sloping? I think they say it has a positive slope. Positive slopes mean that the solid is more dense. So the solid is more dense than the liquid. And that's how it should be for most substances. Where we see that difference, though, is with water. if we were to look at water's phase diagram, here you can see how it slopes this way. That negative sloping line tells you that the liquid is more dense than the solid. So this has a negative sloping line. That tells you that the liquid is more dense. And that's just something else you can pick out. And this doesn't give you quite as much information in terms of pressures and temperatures, but again, there's the triple point, here's the critical point, this would be the solid, the liquid, and the gas. And so we can still pick out different phase changes and things like that from these diagrams. Okay, last problem here. As intermolecular forces increase, what happens to each of the following and why? So I want you to take a second and pause this and see if you can answer these questions. Will it increase, decrease with an increase in intermolecular force? See what you can figure out. Okay, boiling point. As the intermolecular forces get stronger, the boiling point should go up. It should become harder to change it from a liquid to a gas because there's greater forces holding them together. Viscosity should also increase because they're being held together more. They're not going to flow as easily, so they're going to appear more viscous. Surface tension should also increase. Again, molecules are being held more tightly together. There's a greater attraction between them, so the surface tension is going to be higher. The enthalpy of fusion, that's the energy it takes to melt it, kind of the same idea with the boiling point. The stronger your intermolecular forces are, the harder it's going to be to melt it because of those strong forces and having to overcome them. The freezing point is going to increase. And that one takes just a second to think about, but freezing point is where it goes from a liquid to a solid. And if you have a substance that's very attracted to itself and it has a lot of, we'll say, hydrogen bonding or just stronger intermolecular forces acting between the molecules, it's going to kind of help itself out in terms of going from a liquid to a solid because it's going to be really attracted. It's going to pull those molecules in tighter together. They're going to be held closer, so the freezing point should actually go up. It should freeze sooner at a higher temperature. Vapor pressure will go down. Vapor pressure is going to go down because those intermolecular forces are going to hold the molecules together, not allowing them to go into the gas phase, not allowing them to become vapor. The heat of vaporization follows the same rule as the enthalpy of fusion because this is also the heat of fusion. So the heat of vaporization, the energy it takes to vaporize a substance should go up because you have a greater attraction between those molecules. So this is a very important concept. You need to be able to take this idea of intermolecular forces and you need to apply it and use it to explain these different trends or observations that we see. That is it. We just did the entire chapter. So make sure that you took notes as we went. Come to class with questions, and we will do some more practice with identifying types of intermolecular forces and predicting how they will change different properties that we see about substances.